Hey everyone, we're getting started today with our concepts review for Chapter 10. There is only one concepts review for Chapter 10, so this is going to be, it's going to encompass the entire chapter. So, you should probably strap yourself in and get ready for one that's going to be on the longer side. So, let's get started. Okay, here we get started, and we'll read this first question. We've got if f of x is equal to the summation of, well, you can definitely read that yourself, I think. What values does this series converge? Yeah, it's pretty straightforward. Quick strategy, see if that's a geometric series first. If it's not a geometric series, then go ahead and use the ratio test. If it is a geometric series, then the ratio needs to be less than 1. B, write the first three terms and the nth term of the series representing f of 1/4. So that's literally just substituting 1/4 into the series in the problem. I don't think that's going to be too difficult. Letter C, evaluate f of 1/4, relating it to the appropriate Maclaurin series. So for that one, it seems like we're going to have to, first of all, substitute that 1/4. And second, we'll look up that in either the table of Maclaurin series, or we'll try to see if we have that one memorized. And we'll just set it equal to what it is. And lastly, write the series expansion for f prime. So that's a term-by-term differentiation. And then substitute 1/4. Seems like a pretty straightforward problem, or very typical of what you would expect from the AP test anyways. So, part A. All right, so notice that if we write out the first three terms, we can tell right away that this isn't a geometric series. If I grab the mouse here, notice over, we've got 2, that goes to 3, and that's not a geometric function. I mean, we're not multiplying. There's not the same thing to multiply to get from a denominator of 1 in the first term to a denominator of 2 in the second term to a denominator of 3 in the third term. That's just not one of our, that's not the way geometric series work. This puts us squarely in the realm of having to use a ratio test. So what we have here is we're starting by writing down the actual ratio test. This is what, that by definition, our ratio test is. Here we're substituting. We've incremented all of our n's to n plus 1 in this first factor. And in this factor here, that's just a reciprocal of the general term. And I always like to force this less to 1 in these situations because I want to know for what values of x does that ratio become less than 1. Next, you're going to see, over here I've left that the way it is. That's just the definition or the actual ratio test mechanics. On the right side, I've done some simplification. So you'll see that the n over n plus 1, I'll keep those together because, well, they are related. And then, because I'm in absolute values, this negative 1 over here and this negative 1 over here, regardless of what their power is, if I take an absolute value, I'm just going to get 1. So, in essence, I've discarded it, but you don't even need to think about it that way. You just took an absolute value. And lastly, we've got 2x to the n plus 1 over 2x to the n. If you've been following along in class, you know that that's going to cancel out. 2 to the n power, or the n powers are going to cancel. And you're just going to left with this 2x over here. And I put it over the 1 just because I already had the fraction bar set up, and I got to put it on something. And again, you're going to force that to be less than 1. Moving that forward a bit, you'll get, well, this 2x doesn't need to be part of the limit since there's no n there. No n, so we take that out of the limit. And over here, n over n plus 1, well, this limit as n approaches infinity is just 1. So in essence, you just get absolute value of 2x is less than 1, which is pretty close to the form that we want. I would probably take an extra step and write the absolute value of the absolute value of x is less than 1/2. Okay, that's a little bit better. And here we go. The absolute value of x is less than 1/2, which means that x needs to be between -1/2 and +1/2. And this is a key concept. That's for absolute convergence. Now the series might still converge at -1/2. It might still converge at +1/2. We need to test that, which brings us to endpoint convergence. So what happens when x equals -1/2? Well, if you substitute a -1/2, you would basically just substitute that right here. And if you do a -1/2 times 2, you get -1. That's all you need to do, just a simple arithmetic here. That -1 to the n power, well, that's the same thing as this -1 to the n minus 1 power. If you multiply those together, you would add the exponents. So you would get -1 to the 2n minus 1. So this series is actually the same thing as a -1 to the 2n minus 1 multiplied by 1 over n. Which, let's face it, 2n minus 1 is always going to produce a result that is odd. And if you have a result that is odd, or -1 to an odd power, it's always going to be -1. So this series is the same thing as -1 over n. Now, if you don't believe it, go ahead and write a few terms out, and you'll see. You'll just get the series of -1 over n. In fact, I just went and wrote it out for you. -1, -1/2, -1/3, -1/4. So that is the negative of the harmonic series. So this series is negative harmonic series, and it's a diverging series because p is equal to 1. Okay, so our result number 1 is when x equals -1/2, we get a diverging series. Well, what happens when x equals 1/2? Again, you're going to substitute that again. Here, 1/2 times 2 is just 1, which is where this 1 comes from over here. And then this right here, simplified, that's just an alternating, well, it's an alternating harmonic series now, isn't it? So for an alternating series, in order to test whether or not it converges, you can use the Leibnitz test. So the Leibnitz test says that if the absolute value of each term goes to 0, then your alternating series is going to converge. Now be careful, because that's really similar to the, what is that one called? The nth term test. But this is not the nth term test. I recommend you write down exactly which test you're doing so that you're not confused. Okay, here is our nth term. Here is our, sorry, I even did it just now. There's our Leibniz test. And yeah, the series 1 over n, that goes, all the terms of that series are going to 0. Therefore, we're going to get convergence. So Leibniz test, if you don't remember that again, the Leibniz test says that in an alternating series, if the absolute value of every term goes to 0 as n approaches infinity, the alternating series is going to converge. So in conclusion, we're going to get our series is going to converge for x greater than -1/2 and less than or equal to 1/2. So this is a conclusion written in two ways, one time in set notation, once in algebraic notation. I'm a fan of the set notation personally. So here's our conclusion for letter A. We have a series that converges for x between -1/2 and 1/2, inclusive of 1/2. For part B, let's write the first 3 terms and the nth term for the series of f of 1/4. So what happens to the series when f is 1/4? All you really need to do is take the series and substitute 1/4. And here I've gone ahead and substituted 1/4 into the sigma notation. And then now I'm going to use that sigma notation. We'll simplify. Your left side over here, like I've been doing, this is just the same series function that we started off with. These are the same. And I'm only simplifying on the right side. So on the right side, you have 1/2, 1/2 to the n. You can break that up as 1 to the n over 2 to the n. 1 to the n is just 1, so you do nothing there. But 2 to the n, well, that is something. So that can just go right into the denominator because this is 1/2 to the n. Moving forward from here, we'll write down all the terms, or as many terms as we can. 4 is usually enough. Here are the first 4 terms. And that's really all you need to do with this one. Here are the first 3 terms. We did 4 terms, but, you know, a little extra there. So for part C, evaluate f of 1/4 by relating it to the appropriate Maclaurin series. Again, we're going to take the approach, what happens when x equals 1/4? And when x equals 1/4, if you substitute everything in correctly, you'll get this series over here. I want to note to you that over here, if you substitute 1/4 into 2x, you're going to get 1/2 again. That's where these 2's come from on our denominator. So what is this series? And this is going to be a little bit awkward, but from the series table of series, you're supposed to have a bunch of them memorized. And frankly, this isn't one of the ones that I recommend students to memorize. This is like going above and beyond. But this is the series of 1 plus x, natural log of 1 plus x, evaluated when x equals 1/2. So if you have that part memorized, then of course this series is just equal to the natural log of 3/2. Finally, write a series expansion for f prime and evaluate f prime of 1/4. So the trick on this one is to make sure that you take the derivative before you substitute that 1/4. So in this one, the style that I'm going to use is I'm going to take the derivative of the general term. You could absolutely substitute or take the derivative of term by term, but I think it might be easier to see what's going on if we take the derivative of the general term in this case. So let's take the derivative. I notice that this part right here, the -1, there's no x there, and I'm taking the derivative with respect to x. The n over here, there is no x here, taking the derivative with respect to x. So both of these two act like a constant. In fact, the only thing I need to take the derivative of is 2x to the n power. Now be careful when you do this, because this is a chain rule. You're going to use the power rule for 2x to the n, and then you're going to use a chain rule to take the derivative of 2x. So you'll get this n multiplied by 2x to the n minus 1 multiplied by the derivative of 2x, which is just 2. Simplifying this, you're going to notice a couple things that are going to happen. First of all, you know that the n's are going to cancel out, this n and this n here. Secondly, you have the 2. That's just a constant. It really has nothing to do with the series. There's no n involved with the 2. So I just put that in front of the series. And then the last thing I noticed is n minus 1, both the -1 and the 2x are raised to the n minus 1 power. So if two things are raised to the same power, then you could multiply them and put the product to that same power. So when you take the derivative, you get 2 times this series of -2x to the n minus 1 power. Okay. For me, that seemed pretty intuitive to do. You might, of course, find things a little different for yourself. You probably will. If you write out those terms, and if you had taken a term-by-term differentiation, you probably would have gotten to this as well. So here is everything written out. And then take a look at these terms. This is 1. This is negative 2x. Okay. So to get from here to here, I needed to multiply by negative 2x. Pretty easy to see. Now to get from negative 2x to positive 4x squared, I needed to multiply again by negative 2x. And if I multiply by another negative 2x, I get negative 8x cubed. All of this is to say that what you're looking at is 2 times the geometric series. The geometric series part has the first term of 1 right over here, and the geometric ratio being negative 2x. Well, if I'm substituting 1/4, negative 2x is going to be negative 2 times 1/4, which is negative 1/2. So what you see here is a first term is 1, and geometric ratio is negative 1/2. So this series should add up to 2 times first term over 1 minus r, which is 2 times 1 over 1 plus 1/2, which of course is just 4/3. So there we go. F prime of 1/4 is 4/3. Okay, number 2 says that if we have the function with derivatives on the interval 2.5 to 3.5, and there's a list of derivatives here, all evaluated at 3, then write the second order Taylor polynomial for f of x. Now, you want to start off with the general format for any Taylor polynomial. So here it is. This is for any second ordered Taylor polynomial. Actually, this is a Taylor series. The polynomial would just be truncated at that second ordered term. So here we've replaced all of our c's with 3. Since all of our derivatives are being evaluated at 3, our c is 3. And then the next thing you need to do, and probably the last thing you need to do, is just to substitute for all of those f primes, and f double prime of 3. And that's our answer, really. Is it necessary for you to simplify that into minus 3? No, I don't think it is. Part B, let's evaluate f of 2.7. So you're taking your result from part A, substituting a 2.7, and then simplifying. Okay, everything. 2.7 minus 3 is negative 0.3. And you get 8.44. Next, notice that this series right here was not a Lagrange, or not an alternating series. Okay. If it was an alternating series, then I can use the alternating series bound. But the fact that it's not an alternating series means that I need to use the Lagrange error bound. Remember, it's one or the other. I mean, it's not actually one or the other. You can always use the Lagrange error bound. It's just that if you have an alternating series, it's much easier to use that alternating series bound. So we tend to favor that. Okay, so the Lagrange error bound, what is a Lagrange error bound? And that is this definition right here. First of all, you'll notice that I've written this is error, and error is the same thing as the function evaluated at 2.7 minus the polynomial evaluated at 2.7, absolute value of. So that's less than the maximum of the third derivative multiplied by, well, wherever we're evaluating our function, minus the center cubed, multiplied by, or divided by the third factorial. So you're going to have numbers here for this maximum. You're going to have a number here for x1, and you're going to have a number here for c. In fact, I can tell you c is 3, x1 is 2.7, because that's where we are evaluating our function. And the maximum of f3, if you go back to the problem, the maximum of that third derivative is just 36. So the absolute value of the third derivative is less than or equal to 36. That's saying that the maximum of the third derivative is 36. So boom, substitute all of that stuff into your expression, your Lagrange error expression, and you get the error is less than 36 multiplied by this mess over here. All of that simplifies to 0.162. Lastly, what if I looked at this g function, which is x squared f of x plus 3? Now, I know that you're probably feeling like you need to take the derivatives, start over with the Taylor series, and do the entire thing. But I'm telling you that that's rarely the case, especially on the AP test. Now, much more likely, you're just going to substitute things in and then simplify out. So that's what we're going to do. We're going to substitute for f, and then in f, we're going to substitute an x plus 3. Here's what I mean. The x squared, of course, is the same x squared. And then here's f of x, but every time I saw an x, I snuck in an x plus 3. Notice that that simplifies really nicely. X plus 3 minus 3, that's just equal to x. And then when you distribute the x squared, you get this nice polynomial for g of x. You see, really it's not supposed to be incredibly difficult for you to do all of these series problems. The differentiation, the integration, they are meant to be minimal, except, of course, in the most difficult of problems, which, when you see it, you'll probably know this isn't it. So here's what we got for number 2. We have the second ordered Taylor polynomial. We just saw that in letter D as well. Letter B, we said that the f of x is evaluated at 2.7 is 8.44. I'm looking at this and I'm noticing this should really be f of 2.7. We'll fix that for you in the answer key. And B part 2, the error is less than 0.162. If you, what is this one? Let h be the function. Okay, so we didn't get to letter C. Let's look at letter C next. So for letter C, you're given this information that h of 3 is negative 2, and then all subsequent h derivatives are going to be the same thing as f. So for example, h prime of 3, that's the same thing as f of 3 over here. H double prime of 3, that's the same thing as f prime of 3, which is negative 3. F triple prime of 3, that is the same thing as f double prime of 3, which we were told earlier is 12. Now we don't know what f triple prime of 3 is because we were just given a bound. So we don't know what the actual value is. So let's put up the general form for any Taylor polynomial first, and then we're going to start substituting things. Here we've substituted C was 3, and we've changed all of our f into h's. And then lastly, we're going to substitute all of our h's. Notice that h of 3 was negative 2, so we put a negative 2 down over here. H prime of 3 is 7, so that's where this 7 came from over here. H double prime is 3, so this is where the 3 comes over here. Notice that you have to divide it by 2 factorial. And then finally, H triple prime is 12. And then 12 divided by 3 factorial is 2. So here's our answer for letter 2C. Okay then, so we have one more problem to do. It's this one. Here's our f of x, and if you feel intimidated looking at this series, I don't blame you. even me, looking at that, I'm like, ugh, what is this long? And then look at this general term. My gosh. Part A says, what happens when, well, you want to show that the general solution to the differential equation of y double prime plus y equals 0. So you're saying that if you take two derivatives of f and you add it to f itself, you should get a 0. Then there's a domain, and then finally write a closed form expression. That basically means not a series for f of x. So let's go right into it. Here is a function. Y is the same thing as f of x, so I just rewrote it. I'm not actually going to use this general term. I think for a problem of this difficulty, the general term, nice, but no, we'll get more mileage out of the actual terms. So first thing, take one derivative. This is just a polynomial, so there shouldn't be any surprises about how to do this. Notice that I'm not actually simplifying anything. I don't know if that's for better or for worse, but it's a habit of mine not to simplify until I need to. It's easier to see patterns if you don't simplify. Let's take another derivative. Here we go. And then now I wish I did simplify, because I take a look and that's 3 over here, and that's negative 6 over 2. And I know damn well that's 3 is the same thing as 6 over 2. Same thing with 5. 5 is 30 on 6. Okay, so maybe I should have simplified. Next, well, yeah, let's simplify. After that, well, the function or the question asks for y double prime plus y. So let's do that. Let's take our series for y and add it to the series for y double prime. And this is what you get. It's a very, very cumbersome expression. It took 2 whole lines here. But you'll notice that the first terms cancel, the second terms cancel, the third terms cancel, the fourth terms they cancel, the fifth term they cancel, the sixth term that cancels also. So you just get a 0. Okay. Now for these problems that seem super difficult, oftentimes you're just really taking the derivative, sticking it together, and then going for it. It takes a little bit of guts to get through this. You're not always going to feel like you're doing the correct thing, but that's often what it takes to do these math problems. Just go get it done. So, yeah, y double prime plus y is equal to 0. Well, how about the domain of f? If you look at this function, is there anything here to suggest that there's a number I can't substitute? And no, it's just a polynomial. And the domain for any polynomial is all real numbers. So the domain for f is just all real numbers. You can write that literally with the words all real numbers. You can use set notation. X is a element of all real numbers, as long as you get the point across. Lastly, write a closed form expression for f of x in terms of basic functions. And basic functions mean functions that you've met already, nothing crazy esoteric. Okay. So here's what we're going to do. We're going to regroup f of x by their powers. And by their power, I mean is I'm going to stick all the odd powers together, and I'm going to stick all the even powers together. And I notice something. I notice that all the odd powers over here on the left, these all have a factor of 5. And all the even powers, they have a factor of 3. So out of this first grouping, I'm going to factor of 5. And out of the second grouping, I'm going to factor out of 3. The other thing I'm noticing is these denominators look familiar. They should look familiar because they are factorials. 1 factorial is 1, 3 factorial is 6, 5 factorial is 120, and bonus points if you knew that the 7th factorial is 540. Same thing over here, 2 factorial, 2. 0 factorial is 1, 2 factorial is 2, 4 factorial is 24, 6 factorial 720. So when you substitute in those factorials and you substitute out the common factor, you get this expression. And doesn't that look familiar? Alternating series, odd powers, odd factorials. Alternating series, even powers, even factorials. You recognize it yet? That's 5 sine plus 3 cosine. There's no good way to coach you how to do this. You have to really have those cosine and sine factorials memorized. If you don't have them memorized, you really don't have a shot at this kind of a question. You have to have them memorized. You need to be very familiar with what those look like. So here's question 3, all completely done. And we are finished today. Hey, look, I know that was difficult. I know that there was a lot of series problem here where they really compressed the entire chapter down into one sheet. But those problems look a lot like what you're going to see on the AP test. Difficult problems that you would see on the AP test, really. So we're all better for it, and I will see you next time.